Hello everyone, welcome back to another Signals and Systems video. Today's topic is the inverse Laplace transform. Specifically, we're going to look at doing inverse Laplace transforms using the partial fraction expansion and focus on the case where we have complex poles. In this video, I'll show you one method for taking the partial fraction expansion with complex poles, and in another video, I'll show you an alternative method. Okay, let's get started. So, the function that we're trying to take the inverse transform of is f of s, shown here on the left, and ultimately we want to get to an expression for f of t, the time function associated with that Laplace transform. And in order to do that, we're going to use partial fraction expansion, which basically allows us to split this term up into a series of simpler terms that we already know the inverse transform for. So in order to solve for the partial fraction expansion, we first have to solve for the roots of the denominator of this equation. So let's do that. It's fairly easy to see that there's one root or pole at s equals 0, and then it's easy to see that the other two poles, since this will be a third order equation in the denominator, will be at the equation solved by s squared plus 10s plus 34 is equal to 0. So we can use the quadratic equation to solve for those roots, and that will give us s is equal to minus 10 plus or minus square root of 10 squared minus 4 times 1 times 34 over 2 times 1. So s is equal to minus 10 plus or minus square root of 100 minus, write that a little more clearly, 100, wow, that didn't help. 100 minus 4 times 34, which is 136 over 2. So I can write that as minus 10 plus or minus square root of negative 36 over 2, which easily reduces to minus 5 plus or minus 3j. So clearly these roots are complex. We have a complex conjugate . So complex conjugate pair of roots or poles of f of s, and we were guaranteed actually that the roots would be in complex conjugate pairs because all of the coefficients here are real. Okay, so now we have the roots of f of s, of the denominator of f of s. We have a pole at s equals 0, and we have poles at s equal minus 5 plus and minus 3j. And so now we can take the inverse, we can use partial fraction expansion. So let me rewrite f of s. F of s is equal to, now that we've solved for the roots, we can rewrite it as 6 times s plus 34. The numerator stays the same. Now I'm just factoring the denominator. So I have s times s plus 5 minus 3j, s plus 5 plus 3j. Okay, so that gives me my pole at s equals 0, a pole at minus 5 plus 3j, and a pole at minus 5 minus 3j. So now I can use partial fraction expansion and rewrite f of s as a over s plus b over s plus 5 minus 3j plus c over s plus 5 plus 3j. Okay, all I did, these are all single roots, non-repeated roots, so I can just write it as a over the first root, a over the first pole, b over the second pole, c over the third pole. And then all I have to do is solve for the a, b, and c coefficients. So we solve for these coefficients using the Heaviside method, or sometimes we call it the cover-up method. And what we do is we know that the equation for A can be written as, well, we just ignore the term associated with A's pole. So we ignore the S term, and then we write everything else. 6 times S plus 34 over S plus 5 minus 3J times S plus 5 plus 3J, and evaluate that at S equals 0. Okay, all right, that works out pretty well. So we'll have 6 times 34 in the numerator, and we will have 5 minus 3J times 5 plus 3J in the denominator. And so these are complex conjugates in the denominator, so what I'll be left with is just the magnitude squared of this complex number. So I can plug in, and I'll have 6 times 34 over 25 plus 9, which is 34. 6 times 34 over 34, or just left with 6. So A is equal to 6. Another way I could have done this, which might have made the math here just a little easier, is I already know what this is equal to. This is S squared plus 10S plus 34. And so, because if I multiply these back together, that's what I get. And so I plug in S equals 0 for S squared plus 10S plus 34, and I get 34. Okay, so that's the A term. Now we have to solve for B, and we do it exactly the same way, only now we're going to be plugging in a complex number. So let me switch pages here so that we can rewrite what's going on. Okay, so we'll have f of s. Well, let me just write out the equation for B. How about that? So B is going to be equal to 6 times S plus 34 over S times S plus 5 plus 3J, and I'm evaluating that at S equal minus 5 minus 3J. Okay, so all I've done, if I look back, I took I ignored this term since that's the pole associated with B, and I rewrite f of s, or the remaining parts of f of s. This top, s times s plus 5 plus 3j. And I get this, and I evaluate it at that first pole, which happens to be minus 5 minus 3j. So now I just plug in. It's complex arithmetic, but it's straightforward to do. So I plug in for this pole, and I get on top, I get 6 times minus 5 plus 3j plus 34 over minus 5 plus 3j times minus 5 plus 3j plus 5 plus 3j. So the minus 5s will, the minus 5 and the plus 5 will cancel each other out. And I'll be left with, on top, 6 times 29 plus 3j, reducing the formula on top. Write that j a little bit better. And on the bottom, I will have minus 5 plus 3j times 6j. Now the 6 on top and bottom here will cancel. So I cancel those. And I'm left with just 29 plus 3j over minus 5j minus 3, because j squared is minus 1. Okay, so this is the formula for B, and I could leave it that way, but actually it will help me later if I reduce it to a more useful form. So I'm going to do that by multiplying the top and the bottom by the complex conjugate of the bottom. So I'm going to multiply by plus 5j minus 3 on top and bottom. And so that leaves me with, on the top, I just multiply through, I get 145j minus 15 minus 87 minus 9j, just multiplying through. And on the bottom, well, these are complex conjugates multiplied by one another, so I just get the magnitude squared of that number, which we actually solved for before. It's 25 plus 9, or 34. So if I reduce this, I get minus 102, plus 136j over 34. And actually, each of these numbers is divisible by 34, so I can rewrite this as minus 3 plus 4j. Okay, so I have b. Took me a little bit of complex arithmetic to get there, but I got there. Now, I could go through and solve for c the same way, right? C is just plugging in for that other pole, so it'll be 6s plus 34 over s times s plus 5 minus 3j, and I evaluate that at s equal minus 5 plus 3j. Okay, but I know automatically that this will work out to be the conjugate of b, so this will work out to be minus 3 minus 4j. And how do I know that? Well, I know that because if I look back, back here, all of the coefficients here are real. Okay, all of the coefficients are real. So I know I'm going to end up with b and c being complex conjugates of one another. So I encourage you to work it out on your own paper. Go ahead and solve for c on your own and show that it is equal to minus 3 minus 4j. Okay, so I now have simple equations for b and for c, and now I can take the inverse transform. I do want to do one more thing that's going to help me out a little bit. I first want to write b and c in their polar form. So b is equal to minus 3 plus 4j. And I can write that in polar form as r e to the j theta, where r is equal to the square root of minus 3 squared plus 4 squared. And that will be 9 plus 16. So it'll be square root of 25, which is 5. And theta is the inverse tangent of 4 over minus 3. Okay, and we want that inverse tangent not to be restricted to the first quadrant. We want it to actually give us the true angle of theta. Okay, so that's what b is equal to. B is equal to r e to the j theta, and then we know c is its complex conjugate, so c will be equal to r e to the minus j theta. Okay, so knowing that makes our life a little bit easier, so I'm just going to plug in 5e to the minus j theta and 5e to the j theta. And we remember what theta is, but I'm not going to write that. I'm not going to write out tan inverse of 4 over minus 3 every time. So now let me rewrite f of s, and let's see how we can take the inverse transform. Okay, so f of s, now we can rewrite, is a over s plus b over s plus 5 minus 3j. Oh, sorry, s plus 5 plus 3j plus c over s plus 5 minus 3j. Whoops, I think I reversed how I defined those. So this was a minus, and this was a plus. Okay, and I know that a is equal to 6, and b is equal to 5e to the j theta, and c is equal to 5e to the minus j theta. Okay, so now I just have to take the inverse transform of these terms, and so I'm going to use the transform pair that we know already, and that is that 1 over s minus p is equal to e to the pt u of t, where p is the pole location. Sorry, that's not an equals, that's an inverse transform. Okay, so now each of these terms is of this form. Each of these terms here is of this form. It's a single pole. In this case, the pole's at 0. Here the pole's at minus 5 plus 3j. Here's the pole at minus 5 minus 3j. So I can just easily write the inverse transform of each of those terms. So the inverse transform of the first term, so now we take the inverse transform of that first term, and we're going to get f of t is equal to a times u of t. Because in this case, p is equal to 0. Okay, so we're just left with the u of t term, plus 5e to the j theta times, well, now it's e to the pt. P is minus 5 plus 3j, and so I'm left with e to the minus 5t e to the plus 3j_t. Whoops. Switched pages there for a second. Okay, u of t. And then the third term looks very similar. The third term will be plus 5e to the minus j theta, e to the minus 5t, e to the minus 3j_t, u of t. Now hopefully we can see that we could maybe combine some of these terms and make this look like a cosine. So let's try and do that. Well, still have the 6u of t plus 5e to the minus 5t times e to the j 3j, sorry, e to the j 3t plus theta, u of t, plus 5e to the minus 5t, e to the minus j 3t plus theta, u of t. Now, this is e to the j plus something plus e to the j, e to the minus j something, all right? So that we can rewrite as a cosine. 6u of t plus, now we have to have plus 10, right? Because cosine, the definition of cosine is e to the j omega t plus e to the minus j omega t over 2. Okay, so we have to multiply by 2 here, and we've got 10 e to the minus 5t cosine of 3t plus theta, u of t. That is our equation, and we know what theta is. So we can summarize this on the following. We can write this as f of t is equal to 6u of t plus 10 e to the minus 5t cosine of 3t plus theta, u of t, where theta is equal to tangent inverse of 4 over minus 3. Okay, so that's our equation, and all we had to do was do the partial fraction expansion with non-repeated roots, although they were complex, so that made our algebra complex. It included real and imaginary numbers. And then take the inverse transform of each one of those terms and then combine them back together to put it in the form of a cosine, a phase-shifted cosine. And we know what the phase shift is based on the value that we calculated for theta. All right, so this concludes our video on partial fraction expansion with complex poles. Again, it's a fairly straightforward process, but it does involve complex arithmetic. I want to point out one more thing. If you look in MATLAB, you can use the residue function. You can read up on that doing help residue. And residue will get you exactly these complex poles that we solved for. So I encourage you to try that. It's a great way to check your work and make sure that you've done all of your complex arithmetic correctly. Okay, so that concludes our video. If you want more information on the class or the university, you can go check out Okay, so that concludes our video. If you want more information on the class, ECE 220, or the university, you can go check out these various websites. Thanks for watching.